previous video, we have learned how to construct a hyperplane from a linear combination of vectors. In this video, we are going to use this knowledge to easily understand all the situations of linear system solutions. From your analytical geometry class, you must have already learned that a linear system can have one solution, no solution, or infinitely many solutions. You probably also know that the number of solutions is related to the relative positions among the hyperplanes represented by the linear equations in the system. For example, with a three-variable, three-equation linear system, each equation represents a plane. If the three planes are positioned as in figure 1, the system has one solution. If they are positioned as in figure 2 and 3, there is no solution. If they are positioned as in figure 4, there are infinitely many solutions. When we have more equations and more variables, the number of positionings of the hyperplanes grow exponentially. And even worse, they can no longer be imagined easily. So from equation perspective, to look at solution profiles geometrically becomes unrealistic. So let's switch to the vector perspective. An example of rewriting a linear system into a combination of vectors is shown here. On the left side of the equal sign, the three vectors span a hyperplane. Then we only need to know whether the vector on the right side of the equal sign is in the hyperplane or not. If it is in the hyperplane, then the system will have at least one solution, otherwise no solution. Is the right side vector in the hyperplane? From our previous video, we know that three vectors can span a 3D space, but there is a restriction. These three vectors has to be independent from each other in order to span the third vector. In another word, a plane spanned by any two vectors does not contain the third one. The way to figure out vector independence will be introduced in the next video. But for now, let's assume we know whether the three vectors are independent or not and see what happens. If the three vectors on the left side are independent, then they can span the 3D space. The right side vector is already in the space, so there is at least one solution. On the other hand, in a hyperplane spanned by independent vectors, a point in that hyperplane can only be reached by a linear combination of the vectors in only one way. Combining these two statements, one and only one solution can be found. If the three vectors are dependent from each other, then the hyperplane formed by spanning the vectors is a plane or a line. Now, majority of the 3D space is not covered by the hyperplane, so the right side vector can be in or not in the plane or line. If the vector is not in the plane or line, then no solution can be found. If the vector is in, then at least one solution can be found. On the other hand, in a hyperplane spanned by dependent vectors, every point can be reached in infinitely many ways. So combining these two statements, we have infinitely many solutions. In general, a linear system with m variables and n equations can have one solution, no solution, or infinitely many solutions. There are only two deterministic factors. The first one is whether the vectors on the left side are dependent, and the second one is whether the right side vector is in the hyperplane spanned by the vectors on the left side. In the next video, I will describe the process of determining vector independence and whether the right side vector is in the hyperplane or not. Thank you for watching.